Today's webinar is called Outside the Box, Solar Power as a Backup and Hybrid Power Solution. So this is a presentation that I did a few weeks ago in Dubai at the Middle East Energy Expo. And this presentation is really about some creative ways to use solar, some unconventional ways to use solar. So this is a PowerPoint. I'm not sure if all of the animations are going to work here. So just a heads up, some of these slides might not work the way they were meant to, but we will make it work anyway. Okay, so I'm enabling the Q&A mode, which means you can type your questions in the chat box and you can mark it as a question. And then at the end, I can review the questions, and it's easy for me to answer all of your questions. So please, if you have any questions, type them in the chat box and mark it as a question, and I'll be able to answer them all at the end. Okay, so my name is Nick Lusson. I work with Jubaili Bros Solar for East Africa, and I'm based in Nairobi. And let's get started. So this is the three basic topics we're going to look at. We start with basic solar and some hybrid systems and show the difference and what they are capable of and what are some common advantages of some hybrid systems. Then we're going to look at trackers and also bifacial panels. And lastly, we're going to look at floating solar and agrivoltaics, which is solar plus farming. So let's start with basic solar systems. So this is the simplest and most common type of solar system. It is a grid-tied solar system. And yeah, perhaps this isn't the most common. Rural solar might be more common overall, but this is the one that has seen an exponential growth in solar power production. And this is the one that is very, very economically feasible. You can see there the line diagram. All you really need is solar panels and an inverter, and you can supply the grid and power your loads. Now, this is very economically feasible in places that have a stable grid, and especially if the places have a feed-in tariff. So feed-in tariff basically means that the grid will purchase your solar electricity that you don't consume. Any excess solar power you produce can be sold to the grid. That means at the end of the month, your bill could be zero. You could even have a negative bill. There's some countries that would send you a check. You get paid for your extra solar power. Other countries, they don't allow that, but your bill could be zero. So if the grid allows you to feed in, this is very economically feasible. And what you get, this is sort of the load profile of what that would look like. So you see the yellow curve there, that's the solar power produced, and it follows the sunlight, right? Because the sunlight is most intense around 12 and 1 p.m. So that's why the curve looks like that. At nighttime, the bottom there is the hours of the day. So at midnight, 1 a.m., and that's not exactly accurate because the curve actually would start around 7 a.m. But you get the idea. In the mornings, there's very little power production, and then it picks up around noon when the sunlight is most direct. You produce the most solar power, and then in the evening, it goes off. Now, the blue line could be the load. That could be, obviously, it's smoothed over to give it a curve, but this is your consumption. So all those blue areas would normally be the utility power. Now this, yeah, see this one had an animation. So basically, when you're able to sell the power back to the grid, this yellow curve can be applied to the blue parts. The yellow excess solar power, when you sell it back to the grid, it can compensate for the blue areas, and that's how your bill could be zero. Because this yellow excess solar energy does not have to be lost. It can be sold back to the grid. And this is what it could look like. So this would be on a residential system, just roofs on a panel, or this could be a utility application. Because if you're feeding the grid and the grid is purchasing the electricity, it's the same idea. Now let's look at a hybrid system. So a very simple hybrid system is just to add batteries. You can simply add batteries to this system. The line diagram you see is called AC coupled system because the coupling is on the AC side. So oftentimes this requires an extra inverter. You may need 2 inverters for this. You definitely need the batteries, of course. Sometimes this can be done with a single inverter, if it's called a hybrid inverter. Other times you need 2 inverters like what you see. So then what you're able to do is, yes, so similar to the previous load profile, instead of selling the excess solar back to the grid, you can store it in the batteries and use it later. So see, around noon, there's a lot of excess solar energy that is not being consumed underneath that second curve. So with the batteries, you can store your excess solar energy and consume it at night or in the morning or when there's not enough sun. So this could be residential, something like this. It could be C&I, might look like this. Those are battery cabinets next to the solar panels and then next to the load, a factory or something. And it could actually be utility scale as well. So this has been done many times around the world with lithium ion batteries. The biggest ones are over 100 megawatt hours of battery storage. So the reason you would do this, there's 2 main reasons. Number 1 is called arbitrage. This means that the grid can store this energy and then sell it to the consumers later. The reason they would do that is because at noontime, when the sun is shining the most, they're producing a lot of solar energy. And it's very cheap because the sun is free. Then maybe at nighttime, without batteries, they would have to run a fuel plant, for example, a diesel plant, which is very expensive. So if you add batteries on a grid scale application, utility scale application, you can store the energy that is produced very, very cheaply at noon from the sun, and you can sell it later at a higher price during the peak hours because the grid charges the customers according to their time of consumption. So if the grid provider, the utility provider, is able to store the free energy from the sun and then sell it later on when it's peak hours and the price is higher, they can add a revenue to their system. That's called arbitrage. So basically you're storing the cheap energy during the cheap hours and selling it at the peak hours when the price is higher. The second reason that you would do utility scale battery application is called ancillary services. And this has to do with the reliability of the grid. The batteries are able to dispatch power instantaneously at any desired frequency and voltage. So it can correct any problems with the power factor and the power quality. So running your power through a utility scale battery like this can increase the reliability of your grid. it can increase the on time, basically. So you're not losing any revenue from when the grid fails. Also, the customers will be very happy because sometimes their sensitive equipment can be damaged by low power quality if the frequency is not correct or if the voltage is not correct. So by using these batteries, it provides you instantaneous, in the milliseconds. It can provide corrective services in case there's a fluctuation in the grid. The batteries can respond within milliseconds. So that's a very valuable grid service. Now let's look at another hybrid configuration. We can add diesel generators. So now we have the solar, we have the batteries, we have the grid, and we have the diesel generator. And actually the grid is not necessary. This can be done without the grid. It can be just solar batteries without the grid, or solar batteries and diesel without the grid. So the reason that this configuration makes sense, it has to do with the price of diesel and the price of solar. So you can see on this graph, the black line is the cost of diesel energy over the years, and the yellow line is the cost of solar energy over the years. If you check the price of diesel 10 years ago, it was much lower than it is now. And if you check the price of solar energy 10 years ago, it's much higher than it is now. The cost of solar energy has declined so rapidly over the last decade. That's represented by the yellow line. And the cost of diesel, it's always increasing. Even if there's temporary dips, it's increasing. We know that right now, worldwide, the cost of diesel is very high. So if you have a customer, or if you yourself are running diesel generators, that cost is very high. And if you add solar energy, the cost of that electricity is very low. So the idea with this configuration is to change your energy mix to increase the solar energy and to decrease the diesel. So what you get is something like this. So actually, there was another animation on this slide that really demonstrated the savings potential. But basically, if you can see the bottom rectangle that's sort of peach colored, that would be your generator's minimum rated load. So diesel generators have a minimum capacity that they are supposed to run at. You are not supposed to run your diesel generator below the minimum rated capacity, because that can damage the generator. So you see that peach rectangle there is the minimum rated load. So the solar curve is supposed to be as normal with the peak at noon. But with the battery, what you can do is you take the excess, and so this plateau there is the load. It's labeled there, customer power usage. You can see that plateau. So the top part of the solar curve has been applied to the customer power usage, because with this configuration, you can store your excess solar energy, and you only need to run your diesel generator as the base load, the minimum rated load. So you can reduce your diesel consumption by a lot, because you can imagine that this whole customer power usage used to be diesel. All of this used to be diesel. And then when you add solar, everything that is yellow and green is now solar. That's diesel that you did not spend. So it can save you a lot of money, up to 50 to 60% of your diesel generator, your diesel costs. So here is what it could look like. So this is solar. I believe there's some diesel generators there. But you can actually get very creative with solar, and you can add it to almost any other source of power to get hybrid power. So this one is scaled up very big. And when you scale up with solar is when it becomes very cheap. So this is a big site Actually, I believe this is one in Tanzania, and it is 5 megawatts of solar with diesel hybrid. This is the biggest solar diesel hybrid in Tanzania. And this one is solar plus geothermal. Because basically, if you have any power source, whether it's geothermal or diesel or others, there's probably transmission equipment there. You can add solar panels very cheaply and take advantage of the existing transmission equipment. So this is a great way to increase the power production without a lot of the cost. You can add solar power to almost any generation asset in the world. And here is one that is solar plus wind. It's the same idea. So these wind turbines are producing power, and they must have some transmission assets there. You can easily add solar panels to complement the wind, and you take advantage of the existing transmission assets. See, the great thing about solar is it can be placed almost anywhere. You can place it near the transmission assets, existing transmission assets. So before this, it was only wind. And you see those tall towers there are spinning, producing wind. And there's nothing collecting the solar energy on the ground. That is unused land, because they block off this area for the wind turbines. You can't usually access all of that land, but you can put solar panels there and you can collect free energy. So now let's talk about one of the more exciting developments in utility scale solar, and that is tracking systems. Okay, so this is an animation that is not going to animate on this webinar. So what this slide is trying to show you, I know it's very confusing with all these lines, but just notice that all of those panels there are fixed tilt. They all face the same direction throughout the entire day. So those lines, the yellow lines, are representing the motion of the sun. It rises in the east in the morning, and it goes to noon at the top, and then it sets in the west on the left side. So what you should notice is that early in the morning, let's say at 9 a.m. or 10 a.m., the sunlight is at a very steep angle to the panels. That's what those lines are trying to show you. The animation actually showed it very well. But at 9 and 10 a.m., the sunlight is not directly shining on the panels. It has a steep angle, and a lot of the sunlight energy is reflected. And then as the sun climbs in the sky at around noon, you get the direct sunlight, because the sun is high in the sky and the panels are facing the sun directly. You get the most power production at that time. Then the sun in the afternoon gets lower in the sky, and the angle becomes very steep, and it does not produce as much power. So what a tracking system does, now this slide will be almost useless without the animation. Basically, what the animation would have shown you is that early in the morning, let's say 9 a.m., when the sun is rising in the sky in the east, the panels have a mechanism to face east. So they're facing the sun directly. And as the sun climbs in the sky, the panels follow the sun. This gives them the most direct sunlight possible. So the panels follow the sun every day. When it rises in the east, it climbs in the sky and it sets in the west. The panels will face the east in the morning. They'll face up directly at the sun at noon, and they'll face directly at the sun in the west. They're able to move. They track the sun. That's why it's called a tracking system. And it can look like this. So that small solar panel is powering a motor. And you can see the panels are there on a single long bar, and that bar can rotate. And it faces, right now, this could be, the panels are facing east in the morning. Let's say this picture is taken at 8 a.m. and the sun is low in the sky, so the panels face like this. And then as the sun climbs, this whole motor will rotate so that the panels receive the maximum direct angle from the sun every day throughout the course of the day. Now, another application of solar trackers is this. It's called CSP, concentrated solar power. Now, this is different than photovoltaics. This is not PV. This is not PV. This is not photovoltaics. All of those things that look like solar panels are actually mirrors. They are mirrors. And all of them are pointing directly at the tip of that tower. So all of those mirrors have complicated algorithms and complicated tracking systems so that they receive the sunlight and reflect all at the tip of that tower. Thousands and thousands of mirrors will reflect at that tip of that tower. And that means throughout the day, all of those thousands of mirrors are constantly shifting to make sure that they are reflecting directly on the sun, directly from the sun to the tip of that tower. And the tip of that tower has some special materials that are able to get extremely hot. For example, it could be molten salt. Molten salt. And then that molten salt absorbs the heat, and it can get like 1,000 degrees Celsius. It can get extremely hot. And then they use that heat to generate steam from water. They boil water and the steam rises, it creates pressure, and it spins a turbine, and that's how you get power. Now, this is actually more efficient than PV. PV right now has reached about 20% efficiency, around in the low 20s, something like that. This is around 40% efficient, 40. The problem is it's not that common, and there have been some massive failures if they don't take care of the molten salt properly, and it can, when it goes wrong, it can go very wrong. So I'm just showing you this slide and talking about this so you're aware. CSP is concentrated solar power. It's not the same as PV. All of those things are mirrors, and they use very complicated tracking systems. It's much more complicated tracking system than the PV. So let's go back to PV now. This is a solar tracker site in Kenya. This is in Malindi. So I visited this site last year, May. So this is like, I think it's 400 acres of solar panels, and each of them is on a row. You can see the rows. Each of them has an individual motor to face the sun throughout the day. So just east to west every day, it rotates and faces the sun. So here I am at the site. You can see how it is. That entire row is rotating. You see the skinny solar panel on the right side that powers the motor. And then there's some, calculating and management devices there with an antenna, because it receives the signal of how much to rotate the sun. Actually, also something interesting is they have safety features, because if the wind picks up, now on a normal fixed tilt site, the wind is not a major factor, because you can put the panels low to the ground or low to the roof, and you put them pretty flat, only a few degrees of tilt. So the wind is not an enormous problem. But you can see the way they are now on the photo, they're much more susceptible to the wind. So they also have devices that detect the wind speed. And if the wind speed reaches a certain threshold, they go into the stowaway position. They go flat for safety. So this is all built in. It's complicated machinery that tracks the sun. It monitors the wind speed. It prevents damage from the wind. It follows the sun for maximum production, and it can go in a safety position if needed. When you have the trackers, this is what you get. So you can see the image in the top right. Again, apologies for the confusing slides. These are supposed to be animations and it doesn't work on this webinar software. So look at the top right. That gives you kind of a good idea of what the tracking system does throughout the day, that little cartoon drawing. Now look at the load profile. So we have the normal load profile there, the one we recognize, the curve. The other one with the wider shoulders is from the trackers, because what the tracking system does for you is it allows you to reach your peak power production earlier in the day because your panels will face the sun. So at 10 a.m., your panels are facing the sun directly, and you can achieve peak power at 10 a.m. Then, of course, at noon, it's still facing the sun directly. Even at 2 p.m., 3 p.m., you're facing the sun directly, you can achieve peak power production. The fixed tilt, you see the peak only happens at noon. So with the tracking system, this is why it is a good idea, because you get this extra production in the morning and the afternoon. Now, the important part about all of this is it has to be financially viable. We aren't looking for extra production. If it costs too much money, it won't happen. So the thing about tracking systems is see this extra production, it is more extra production than the cost. So that means it's a good value. So that's why it is common. And I'll talk more about that later, and I'll tell you how common it is. But first, let's talk about a different type of tracker. Everything I have said so far is about trackers is about single axis trackers. Single axis trackers. That means there's only one axis of movement. It can only rotate to follow the sun from east to west. That's the only movement that there is. Single axis trackers. But the sun has two movements. The sun goes two directions. So every day we know that the sun goes east to west, or it appears that way from Earth. We know that the sun doesn't move. Earth is the one moving, but from a fixed position on Earth, the sun appears to go east to west. We're all familiar with that. Every day the sun starts in the east, climbs, and goes to the west. But that's not all the sun does. The sun has an annual movement as well that goes north to south. So what you see on the screen there is a picture that is taken from the same place at the same time of day, every day, all year long. So let's say it's at noon. So this picture, you see the position of the sun at noon every day throughout the year. So you see the sun does this pattern throughout the year, and it's at its peak. The highest point in the sky is the summer solstice. For the northern hemisphere, that is June 21st. And the sun is at its lowest point at noon on the winter solstice, December 21st. And then it goes in this big loop so that the equinox, it crosses the same point. So that's in the northern hemisphere, actually in both hemispheres. It's March 21st and September 21st, give or take one day. So that is the annual movement of the sun. And this is basically the reason of summer, spring, and winter and fall, is because of this annual movement of the sun. So here's another image that shows you what it looks like. Again, this was supposed to be an animation. But you can see over this town, east to west. East is at the top of the circle, west is at the bottom, south is on the right, north is on the left. On June 21st, the path of the sun in the sky is very high. And then on December 21st, the path of the sun is much lower and steeper. So the sun has two movements. The single axis tracker only tracks the daily movement, but we have something else called a dual axis tracker. The dual axis tracker can track both movements of the sun. So you see on the left is the single axis tracker. It only has one axis of movement and it follows east to west every day. The dual axis tracker has the ability to follow the sun every day, but also during the course of the seasons, it will remain pointed at the sun. Now, the problem with this is it is very expensive. The single axis tracker provides you additional yield for an additional cost, but the yield is greater than the cost, so it makes sense. The dual axis tracker provides additional yield for an additional cost, but the cost is most often higher than the yield, so it's not common. In fact, there was a study that was published by, I think this was by NREL, the National Renewable Energy Laboratory. Is a very well-known renewable energy think tank. They said that for 91% of the Earth's land mass, a single axis tracker with solar panels is the cheapest electricity on Earth. So I'll say that again. If you look at the globe and look at the land mass and anywhere in the world, for 91% of the Earth, single axis trackers with solar panels with single axis trackers is the cheapest and most efficient power available on Earth. Dual axis trackers only make financial sense way in the north and way in the south, near the Arctic Circle and above the Arctic Circle. That's the only place where the additional yield matches the costs. The rest of the planet, the single axis trackers is the best choice. So this chart here is showing the actual demand and the expected demand of the tracker market in the United States. And this can be applied globally, more or less. So you see the purple is single axis and the blue is dual axis. So you can see both are set to increase quite dramatically, with single axis trackers taking the lead. I think this is actually very optimistic for the dual axis. I think it's going to be less than this, but single axis trackers are mainstream. In fact, in the last, let's say 3 or 4 years, 70% of the new land-based utility plants, solar plants, they use single axis trackers. 70% of the new land-based solar plants, utility scale, use solar trackers in the last 5 years. So single axis trackers are now mainstream. They are mainstream for utility scale plants. Here's a cost breakdown to give you an idea of what it costs. So generally it costs an increase of 35% of what your panels are. So if you can calculate the cost of your panels for a plant, if you want to get an estimate of the trackers, take about 1/3 of the panels and add that. So generally that's about 10 to 15% overall of the overall cost. It will add 10 to 15% of costs, but the yields can be 20 to 25% more, even 30% more. So that's why it makes sense, because you pay 15% more, but your yield is 30% more. So that's why it's a good idea. Dual axis trackers, they can cost up to 40% more. Instead of this 15% more for the single, dual axis trackers can cost around 40% more. And the yield is around 30 to 40, so it doesn't make sense. So now let's talk about bifacial, because this is a new development in the solar industry in recent years. So bifacial panels, if you look at that diagram there, it gives you a good idea of what they are. Bifacial panels are panels that have the solar cells on top and on the bottom. So this means that you can produce energy from underneath the panels and on top. And you might think, why is that a good idea? Because actually there is always light that reaches the underside of the panels. So you can see it here. There is always reflected light that reaches the bottom of the panels. And there is always diffuse sunlight, because the sun is not a torch. Have you ever seen those really high powered torches that only light up one small tube? That's not how the sun works, right? The sun lights up everything. That's because of the diffuse light and the wide angles. So my point is, even underneath this table that I'm sitting at, underneath this table is receiving light from the windows and from the light above me. So it's the same with your solar panels. You are always receiving sunlight on the bottom of your panels. So the bifacial panels allows you to collect that energy and turn it into electricity. So this is what they look like, basically. You can see a couple different examples. And as I've said, the solar cells are on the top and on the bottom. So that's why they produce power on the top and the bottom. Now, one thing that is very important when regards to the bifacial panels, it's called albedo. So when you're designing plants with bifacial, this is one of the very key considerations. And this is one reason that makes bifacial panels difficult, and I'll explain that. So albedo is a measurement of how reflective a surface is. And it's on a scale of 0 to 1. So you can see there, an albedo of 0 means there is no reflected light at all. You can see asphalt there is 0.1, grass is 0.25, desert is 0.4. When you have an albedo of 0.5, that means half of the light is reflected. You can increase the albedo with white painted concrete. You get 0.63. And among the best is reflective roof foil. There's special foil material that will reflect 80 to 90% of the sunlight energy. So the reason that's important is because if you look at this, this is a bifacial installation with asphalt, and the albedo is 0.1. And it is not going to produce a lot of power on the bottom because of the albedo of the environment. Next, we can look at grass. Grass is a little bit better, 0.25. You're going to produce more power from the backside. Next, we can look at the desert. Even more power, the albedo of 0.4. You're going to produce even more solar power on the backside. But you can take it a step further. Here's white concrete. If you can do this on white concrete, now you're really going to generate some significant power. Even the desert is significant. So now you're going to generate even more power. And how about snow? Snow has a very high albedo. You're going to get a lot of reflected sunlight from the bottom that will reach the bottom of your panels. And the best would be reflective foil. It can have an albedo of up to 0.92. So that would be generating a lot of reflected energy on the bottom. But there's many considerations that you need to take into account when you're doing this. So again, this animation is making the slide confusing. But when you're designing with bifacial panels, you need to consider the albedo of the environment, right? I've just explained that, of how reflective the environment is. But also, you need to consider your row spacing. How much space is in between your rows? Generally speaking, the greater the row space, the more reflected energy you're going to get. Also, you need to consider your height, your clearance from the ground. Generally speaking, The higher your panels are, the more energy will be produced from the backside. But there's a cost for all of this, because if you put your panels high, you're going to increase your mounting structure cost and you're going to increase your wind risk. If you space the rows a lot, you're going to increase your land use and therefore your land price. So everything comes with a trade-off. You can generate up to 30% more power from the bifacial, but every site is different. You need to consider the albedo, the row spacing, the row height, your angle also. Generally speaking, the steeper the angle, the more power you get on the backside, but you're going to sacrifice power on the top side. So everything has a trade-off. But the good news is that bifacial panels are now not a big cost addition. The panels themselves are almost the same price. You can see that in 2016, the gap between monofacial panels and bifacial panels was very much. And now you can see in 2022, the difference in price is very little for the panels. So this is why bifacial is becoming mainstream. It's not mainstream yet, but it's becoming mainstream. Here is a graph showing the bifacial market over the next 4 years, next 2 years, I guess. And it's broken down by region. So you can see that most of it will happen in Asia and North America, but it's growing in every region, and it is expected to hit 20 gigawatts in 2 years, 20 gigawatts. Now, if you combine bifacial and single axis trackers, you get a very potent combination. So actually, I misspoke earlier, because when I said that single axis trackers are the best solution for 91% of the Earth, I actually meant bifacial with single axis trackers. This is the combination that for 91% of the land area of Earth will provide you the lowest LCOE of all sources of power. Okay? Bifacial plus trackers is where you get a very big yield increase for a minimal cost increase. So this is something that you're going to see more and more and more. Trackers are already mainstream, and the next step is going to be bifacial plus trackers on utility scale applications. Going forward, this is going to represent the bulk of land-based utility scale solar applications. But now, so we've talked about some considerations of land. We've talked about how land space, you need to consider the albedo, the environment, your row spacing and things like that. But what about any other concerns with land? So now let's talk about agrivoltaics. Agrivoltaics is solar plus farming. Agri, like agriculture, voltaics, like PV, photovoltaics. So there's generally 3 levels of agrivoltaics, three large categories of agrivoltaics. So the first one is just native plant species, like what you see here, because this is very good for protecting ecosystems. If you just allow, or you can even plant endangered species of plants, you can plant them around the solar panels. And if you do it properly, there's no interference. And this creates a safe habitat for these plants. The native species of plants that are often endangered can thrive in the protected area of a solar plant. You can also do beekeeping. You can create beehives and let the bees enjoy the native species of plant. And this is also very important for our ecosystem. And bees are generally endangered around the world, and they're very important. So this is a stage 1 of agrivoltaics. Oh, here's some beekeepers on a solar site. So the bees are pollinating, they're protecting the environment, and the solar panels are protecting the plants because generally that area is protected. So the next stage of agrivoltaics is animals. You can actually have animals grazing underneath and around the solar panels. And when you do this properly, there is no damage to your solar panels. So you have to make sure you have the right kind of animals. You have to make sure you have the right kind of installation. The cables have to be protected. There has to be significant clearance. But this is very useful for small farmers, right? Because small farmers all around the world are struggling financially. So if you can provide an additional revenue through the solar panels, this can protect their small farming. And this is, again, very important for the economic well-being of large populations of people. If you can provide additional income for the people that own the land and graze the land, it's fantastic. So here's another picture of some animals grazing. And then the third level of agrivoltaics is with crops. So you can grow crops underneath your solar panels. There are many crops that will grow better with the partial sunlight provided by the solar panels, the partial shading. These are usually the leafy green vegetables like spinach, skumawiki, lettuce. These type of leafy green vegetables prefer partial shading. If you add solar panels to your leafy green vegetable garden, you will get an additional yield of the vegetables. You will have greater crop production. You will have more spinach, more lettuce than if you remove the panels. Plus, you get the added revenue of the solar panels. So this is very interesting in a lot of places. This is a new development. It's only a few years old. It's still being tested, but what it has proven, the solar panels can increase your water retention in the soil up to 200%. The soil retention of the water, the water retention of the soil. That means if you're irrigating, you can use less water. That saves you money. This also means it increases the growth season because the earth does not dry up so fast. So that provides you a few extra weeks of growth time. So this is actually very beneficial. And I read a study that said, so lettuce is one of the vegetables that works very well with this scheme. In the United States, if we covered all of our lettuce farms with solar panels, that alone would be enough power for the entire United States. And we would have more lettuce, cheaper lettuce. So this is a very interesting development that there's a lot of new research on. So this is what we call dual use of land for agriculture and solar. Well, what if you could avoid land entirely? No land use at all. Here you go, floating solar. You can have your solar panels floating on a body of water. Now, this has several advantages, and one of them is no land costs, no competition for the use of the land. This is very good, especially if you have a body of water that is privately owned. You don't need the land permits. It's very easy to do. And oftentimes, there's nothing happening on the surface of the water, right? It's unused area. So there's no competition. There's no opportunity cost. You can simply put the solar panels. And it generally looks something like this. You have to have the floating pontoons for the solar panels. They have to be anchored. They can be anchored at the bottom of the water or to the shore. On the screen, it shows that the inverters are floating on the water. That's optional. Sometimes the inverters are on the land. But you get the idea. It's very similar to the land-based solar. It's very similar. Maybe a few extra safety features. You have to consider the floating structure and the anchors. The rest is the same. Now, this has several benefits. So actually, this, what you see on the screen is a cost breakdown. You can see that the floating PV structure, there's extra design considerations and extra costs. It can be about 10% more. However, when you have a floating solar plant, let me go back here. If you have a floating solar plant, this will produce more power than the equivalent system on land. Why is that? It's because of the temperature coefficient. So solar panels are very temperature sensitive. When a solar panel becomes hot, it will be less efficient. All right. If you look at the data sheet of all solar panels around the world, if you look carefully, they will have a temperature coefficient, and it will tell you for every degree of Celsius that the panel increases, the performance will reduce by a certain percentage. So when you have a floating solar structure like what you see here, the water provides a cooling effect. And the wind also, the water and the wind combined, they keep the panels cooler, at least 1 degree Celsius than the same system right on the land. So this means you're getting extra yield. So that's very interesting benefit there. So this is the rising demand of floating solar installations around the world. So the blue bar is how much was installed every single year, and the orange line is the cumulative installed capacity. You can see that's a very steep increase, and that's only to 2018. 4 years later, you can imagine it's continuing on that trajectory. So here's a map of countries that have floating solar installed, and this is increasing every day. Probably this map is missing a few countries. Now, here's what's very interesting. Floating solar plus hydro dams. Because hydropower, I'm sure we're familiar with it. Generally, there is a dam that holds a lot of water. And the hydropower controllers are able to release water as they determine fit. And that water falls out of the dam and it spins a turbine and it produces power. That's how hydropower works. You store water up in a dam. There can also be run-of-river hydro, but let's talk about the dams right now. The dams have turbines and they have control valves, and the operators are able to release water very accurately to produce the power that they need. Now, what this table on the screen is showing you is that for all hydropower dams around the world, you can double the power generation capacity by adding solar, floating solar, and you would only cover around 4% of the reservoir. So let me say that again. For all dams around the world with the hydropower dams, you can double the power generation capacity simply by adding floating solar to half of, to 4% of the reservoir. 4%. In fact, look at the table there. The column on the right side is showing how much percentage of the reservoir is needed. 3%, 1%, 2% to double the hydropower capacity. So this is a very, very interesting synergy. And in fact, here's some more. So if you're able to install floating solar on a hydropower dam, first of all, you're using unused space. Nothing is usually happening on those reservoirs. Number two, you are maximizing the existing transmission assets. So you can, you don't need to install new transmission assets. You can connect to existing transmission assets. So you can smooth the PV variability. They can work together with the hydropower and the solar, and you can adjust the hydropower very accurately to adjust the variability of solar, because when clouds come and things like that, the power goes like this, up and down, up and down, up and down. So you can smooth it out with the water, the hydropower. Also, this allows you to operate at night because the hydropower can provide power at night. So the solar can provide power during the daytime, the hydropower at night. Also, there's seasonal benefits when you consider the rainy season and the dry season and the wet season and things like that. Also, the solar panels will reduce the speed of evaporation. So you're not losing water just by evaporation. That means more power can be produced because the water remains longer. Also, when you think about it, the reservoirs become a giant battery. Because when there is water in the reservoir, it is a battery. It is stored energy, and you can produce the energy whenever you want. It's a battery. So the hydro reserve becomes the battery for solar. And in fact, the biggest problem of solar is that it can't produce at night. That's the biggest problem of solar energy. It needs a storage mechanism. So if you can combine solar and hydro, it's a perfect match. And it gets even better because there's something called pumped storage hydro. So you can actually use the solar panels, the floating solar, and pump water into the reservoir. And it becomes a battery, and it's storing the energy. And you can do this in the daytime when the solar energy is extremely abundant. And you can store that hydro energy and use it when you need it. And the round trip efficiency is above 80%. That means of the solar energy that is consumed for pumping, you can return 80% in the form of electricity. And that's very good. If you can use the abundant resource of the sun, the unlimited resource of the sun, and you can store it in an existing hydro dam at 80% efficiency, it's amazing. To me, this is the solution to the world's energy problems. Solar plus hydro storage. Even using existing dams around the world, you can double the capacity with the solar panels. You can turn it into a pumped storage hydro system. You don't even need any other power source. So here's a picture of one floating solar on a hydro reservoir. Here's a much smaller hydro reservoir with floating solar on it. Here you can see it's connected to a dam, just like we've been discussing, floating solar on the water reservoir. And here is another one. So in fact, this one, the floating solar is so small, you can barely see it because it's like 1% of the entire reservoir. So that is actually the end of this presentation. I went much longer than I thought. I went in more details. So I hope this was informative. I hope you learned something. Maybe it raised some questions and you can do more research. So now let me have a look at the questions here and we can go through them. Okay, so let's start with a question from Jesse. Let me go to the questions. Okay, he says, we can use solar PV in other power plants for auxiliary load. How can we motivate more power plants to pick up this idea? That's a good question. I think it's really a problem of getting to the decision makers with an accurate financial projection. I think that is the obstacle, and that's not a huge obstacle. If you can show someone who owns land and maybe owns transmission assets, if you can do a detailed production yield and a detailed financial yield, it makes sense. So to me, that is the biggest obstacle, is there's not enough awareness. And yeah, so it would take a team of experts to be able to do detailed financial projections and show the owners that this makes sense. To me, that's the real obstacle. Okay, I see Jesse had a few more here. Let me try to mark them as questions so that I can publish them. Okay, and I see that someone here has asked for the presentation. All of you will receive this presentation in your slides after this presentation. Okay, so let's see. Osirian Flour Company in Naivasha had installed solar PV as additional to their off-grid geothermal power plant. But sometimes back in 2019, they had a lot of problems from PV power due to its intermittent. Have you considered that also as a study experience from Osirian Flour Company on how to assist them? So I'm not aware of this, but yeah, solar is a bit intermittent because as clouds come, it will decrease your production. And then when the clouds go, it will increase. And that's quite unpredictable throughout the day. If you look at a whole year, you can predict how much power you're going to get. But from an hour to hour, minute to minute basis, you cannot predict where the clouds will be. So I think in this case, based on your question, it would have to be just how the solar was connected and how they relied on it, because the intermittency does not need to be a big problem. Maybe they need a storage system to regulate the intermittency. It really depends. I can't answer this without more information, but the intermittency should not be an obstacle to a hybrid power system. In fact, the geothermal can cover the intermittency of the solar. So Jesse, let's talk after this because that shouldn't be a problem. I'd like to know more information. And floating solar can also be hybridized with pumped hydro storage. Right. So I touched on this right at the end. This is the most exciting thing for me, floating solar with pumped storage hydro. Actually, this is the world's oldest, I wouldn't say world's oldest, but this has been used for hundreds of years, at least 130 years. Humans have been doing pumped storage hydro, where you pump the water and you store it. And when you release it, you pump it back. This is the most mature battery technology, and it's the most used. If you look at the gigawatts of pumped storage hydro around the world, it's by far the number one. Second is lithium ion, and it's this much compared to the pumped storage hydro. Pumped storage hydro is the world's most mature and most used battery technology. We don't always think of it as a battery, but it is. Pumped storage hydro. When I started learning about pumped storage hydro, I got very excited. So if you're interested, please do some research. It's actually amazing.